Hello everyone. This is the presentation video for the ICIP23 paper Mitigating Dataset Bias in Image Captioning through Clip Confounder-free Captioning Network. I'm the first author of this paper, YeonJu Kim. This paper presents a novel method, which is a method that mitigates dataset bias in image captioning through Clip Confounder-free Captioning Network. Image captioning is the task of generating a textual description of images. The dataset is inevitably biased towards certain situations, which provokes the model to generate the caption relying on contextual evidence, rather than visual evidence. The feature in the slide shows the example. We instantiate the samples of people cutting a cake that commonly appear in the training dataset. In this case, the model tends to spuriously associate the word cutting with the image of the people and a cake, instead of the actual cutting action. As shown in Fig. 1b, when the cake and two people co-occur, the model tends to wrongly predict that people are cutting the cake even though they are not. Such failure cases can substantiate that the model is likely to learn the spurious correlation between the images and predicted words due to the statistical dataset bias. To mitigate the statistical bias, several studies have integrated causal inference into image captioning. In the causal approach of the image captioning task, the confounder is the most important variable to be explicitly constructed. It is difficult to explicitly identify the confounder from images, so the previous works approximate them using pre-trained models such as Faster RCNN and GLOVE to define the confounder explicitly. There are two examples here. DIC is based on the front door adjustment that eliminates the influence of unobservable confounders originated from dataset bias. It samples a semantic structure set from ConceptNet and use it as a mediator. CIIC suggested the backdoor adjustment model that mitigates the negative influence of the visual and linguistic confounder. As DIC and CIIC, the confounder and mediator are approximately attained by the features from the Faster RCNN and the GLOVE embeddings. However, the previous works are not sufficient to identify the confounder. According to the backdoor adjustment criteria, the confounder should be blocked to prevent all spurious paths between the image and the caption, thus it has to contain all of the confounding factors. However, the aforementioned pre-trained models are optimized for the upstream task with an insufficient training dataset, so they can only represent the bounded information of the limited objects that are labeled in the training dataset. Our main goal is constructing the information-rich confounders that contain a lot of possible visual representations. Since the statistical bias in the image can be potential confounders, to implant the comprehensive visual information into the confounder, we use the pre-trained vision language model clip and name the constructed confounder as Global Visual Confounder. We propose a novel image captioning model, Clip Confounder-free Captioning Network, C2CAP, which can alleviate the negative effects coming from the statistical dataset bias between the visual inputs and the captions. Specifically, we exploit the information-rich clip to build a predefined dictionary, C2 dictionary, that contains representative confounding factors. After that, we train the transformer-based image caption model conditioned on the constructed confounder dictionary. This is an overview of the proposed method. I'll talk about three things here. First, causal graph. To interpret image captioning from a causal perspective, we first construct a causal graph of image captioning models. Second, C2 dictionary. We have to explicitly construct the confounder first. We utilize pre-trained clip that has rich visual information learned from the large-scale dataset and build global visual confounder into the C2 dictionary that can contain a lot of potential confounding factors in the dictionary. Third, C2 cap. Using the predefined confounder, we train the transformer-based image caption model conditioned on the constructed confounder dictionary. Let's start with causal graph to interpret image captioning from a causal perspective. In the graph, X is a visual feature, Z is a confounder, Y is the caption, and M is the context vector coming from the encoder which has to contain contextual information. The path from X to M is the true causal effect that we want the model to learn. The path from Z to X and M is the backdoor path that causes the spurious correlation between the visual feature X and the context vector M. To block the backdoor path by cutting off the path from Z to X, we utilize the causal inference technique named backdoor adjustment. For the backdoor adjustment, we have to explicitly construct the confounder first. We utilize pre-trained CLIP that has rich visual information learned from the large-scale dataset and build global visual confounder into the C2 dictionary that can contain a lot of potential confounding factors in the dictionary as illustrated in Fig. 3. Then we name the constructed confounder dictionary as C2 dictionary, which means CLIP confounder dictionary. It follows two steps of the building process as Step 1. Extract CLIP features. We obtain CLIP features of the training images with the pre-trained CLIP. Its embedding contains rich information that depicts an abundant visual representation of the corresponding image. Step 2. K-means cluster. Cluster the features using K-means and extract all the centroids of the K clusters. Each centroid represents the potential confounding factors that can be a global visual confounder. The centroid of each cluster represents the potential confounding factors that exist among similar images. This is the global visual confounder we defined. With the C2 dictionary, we can train C2 CAP, which is CLIP Confounder-free captioning network. We utilize the backdoor adjustment to cut off the backdoor path in our causal graph. The following equation represents the backdoor adjustment. However, the backdoor adjustment requires a time-consuming sampling process. Therefore, we use normalized weighted geometric mean, NWGM, to enable approximating the backdoor adjustment. To implement NWGM, we use cross-attention. We fuse visual features and C2 dictionary with the cross-attention and calculate the score matrix using scaled dot product attention to get the aggregated visual confounder ZX. By conditioning on the aggregated confounder ZX, we can estimate Debiased context vectors M. Then, we put the Debiased context vector into the decoder, which is the same as the baseline, to generate the corresponding captions. Eventually, C2 CAP is trained to be free from the negative effects of the confounders and generates the Debiased captions. From now, I'll talk about the experiment. For datasets and evaluation metrics, we did like this. We evaluate our model on the popular MS-COCO dataset, which includes 123,287 images and corresponding 5 annotated sentences. We adopt the Karpathy split, where 5,000 images are used for validation, 5,000 images are used for test, and the rest for train. We use 5 evaluation metrics to assess the quality of our image captions: blue, meteor, rouge, cider, and spice. For implementation, we adopt these things. To create C2 dictionary, we use 123,287 Mega-Siemens COCO dataset images. To augment the dataset, we use rand augment with magnitude 1 to produce 3 more images per image. We cluster them using the K-means algorithm, and K is 1000. For the visual feature, we use the bottom-up features that are extracted from the pre-trained up-down model. For text preprocessing, we convert all letters to lowercase, delete the punctuation characters, and tokenize. For more details, please look at the paper. This slide shows the result of quantitative analysis. In Table 1, we compare our C2 CAP with the SOTA models on the offline MS-COCO Karpathy test split. In Table 2, we conduct ablation experiments to demonstrate the effectiveness of using C2 dictionary. In both experiments, our method efficiently alleviates the negative effects of statistical dataset bias and finally achieves improvements in performance. This slide shows the result of qualitative analysis. We categorize the biased image captions into 3 different types as object bias, action bias, and gender bias. While the baseline model generates biased captions due to the negative influence of confounding factors, C2 CAP generates Debiased captions in whole categories by exploiting the capability of suppressing confounding factors using C2 dictionary. Thank you for listening. For more details, please refer to our paper.